Hello everyone, in this video we're going to discuss on radioactivity. We're going to start with rate of decay. Now rate of decay is dN over dt, right? And the equation is dN over dt equals to negative lambda n. What is this? Lambda is decay constant and the unit is per second or per year or per month or per days. Next is n. What is n? N is number of nuclei present. And what about this negative sign? So this negative sign indicates that number of nuclei start to decrease with time. Rate of decay can also be called as activity A. And the unit for activity is Curie. But Curie is quite big. It's a very big unit. So there's another equation, there's another unit and that we can introduce, and that is becquerel. Now becquerel is a smaller unit and more accurate. So what's the relationship between these two? So 1 Curie is equivalent to 3.7 times 10 to the 10th becquerel. So normally when you do this calculation using this equation, you're going to get the Curie unit and then you can change it to becquerel. Now sometimes you are asked to find activity in terms of time, alright? And you can get that by using this particular equation, that is A equals to A naught exponent negative lambda t. And remember the lambda over here is the decay constant. Not only we can determine the activity at certain time, we can also get number of nuclei with time. And the equation is basically the same shape, except that from activity we change it to number of nuclei. Like that. And there's another one. You can get mass with time. The same shape again. M equals to m naught exponent negative lambda t, where the lambda is the decay constant. Now let's talk about half-life. The equation for half-life, T half equals to ln 2 over lambda. Again, lambda is the decay constant. And the unit can be varies, any unit of time, second, minutes, years, hours, week, days, anything. Now I want to sketch the half-life graph. So this would be nuclei, number of nuclei, and this is the time. We start with the n naught like this, the initial number of nuclei, and then it starts to decay exponentially like this, and half of this n naught is this one. This location is half of the n naught. This will be your first half-life. Okay, and then this would be 1 over 4 of the n naught, and this would be your second half-life. And then if it's half, then a quarter n naught, there will be 1 over 8. This would be 1 over 8 n naught, and that would be the third half-life, and so on and so forth. Now I want to talk a little bit on molar mass or number of moles. So let's say we have this isotope of carbon 11. We have here carbon 11, so the molar mass of carbon 11 is, this is M, capital M. That will be 11 grams, okay, 11 grams per mole. You can also get the number of moles, okay, and that would be mass per molar mass. This one, you might want to change this gram into kilograms. So like that lah, you change it to kilograms if you want to do the substitution right here lah. And then there's another one for equation for number of moles, and that would be number of nuclei over Avogadro's constant. So the Avogadro's constant is 6.02 times 10 to the 23. So that's all. After this, I'm going to show you a little bit of, I'm going to discuss a little bit on questions related to this radioactivity.